So we are still looking at the expression for the refractive index of liquid, and now we have looked at the first idea using a concave mirror. And then number 2, we can now say, let's look at real and apparent depths, using real and apparent depths. And then you can say consider an object or placed at the bottom of a liquid in a container, the object appear to an observer above it as raised to some height, as shown below. Okay, so we are looking at a scenario where you have your liquid in a container, and then you so happen to put an object, any kind of object, below the liquid, at the bottom of the liquid. What is very true is that when you try looking at that object, to yourself it will appear like the object has been raised up, isn't it? You look at it, it's too shallow. So we want now to use that idea to derive something very simple here, that if I have this, what actually happens that when I have object here, what is it true? Rays of light will move from the object, be refracted here, okay, and will be appearing to be coming from here. And this is what we are calling the image now. That if I have this is now my liquid, this is my liquid, that if I have this object here and then someone happens to see it, you will see this object as raised somewhere here. And we're saying that what you are exactly seeing as the object is raised, it is not true, it is just the image of the object. And how does that happen? That light rays from the object will move. When it is now leaving the rays, leaving the liquid and moving in air now to your eyes, what happens is there is some kind of refraction that takes place, but we know that if it is moving from more dense to less dense, the refraction goes away from normal. It moves away from normal. And then what will happen is, if it comes in your eye here, in your own observation, you will not see the refraction, the bending that has taken place. Instead, you'll see things in straight line, isn't it? The propagation of light being in straight line. Therefore, what you will see this light here as not coming from O, but for you will see it as coming direct away from BI. And therefore this object here will be seen to be here. Now, what is very true is that in reality, this is what we are calling the real depths. Okay? And then, what is now apparent, or which looks like, is this. This is what we are calling the apparent depths. It is apparent or relative. It looks like the depth is that. And now, this is exactly, I can call it D, which is what we are calling the displacement. Okay? That it is, in reality, the real depth is this. But now it looks like it is this point. Now the depth is just this apparent depth. It looks like, isn't it? Apparent. But now what is very true out of that is that if the object which is here is now appearing to be here, that means it has been displaced from here to this point here. So D is the displacement by our observation. And what is bringing all this is the effect of refraction. So if I look at reversibility of light to allow me say this is angle I and this is angle R, okay? It will be true that if this is angle R, this one here can as well be R, okay? Hey, could I call them, those are alternating angles? Okay? And then what is very true is that even this one should be our I. If you look at this, if I have something like this, if I have that as I, and then this one also should be I, it looks like it is a corresponding angle at the same point. So this one should also be our I. And then if this is my any, that point I can call it any. Let's see at what comes out next. So we can say applying Snell's law at B. I'm coming now at this point B here, and I'm going to apply Snell's law. So if I'm applying Snell's law here, I'll say refractive index of air, sine of angle in air is I, to be equaling to the refractive index of the liquid, sine of the angle which is in the liquid is R. That is the Snell's law I'm talking about at this point here, B. And then I'll say from my triangle, any IB, this one here, right angled at that point. What is very true is that sine of I will be opposite of this angle here, okay? Any B out of the hypotenuse is IB. And then similarly, from my triangle, any O, that is if I'm looking at this point being O, this is my object. So any OB, I can say my sine of R, okay, is equal to the opposite any B out of the hypotenuse or B. Any B or B. So, if I decide now to substitute all these two in my equation here, okay? If I can call this one equation 1, this is equation 2, and then I can say substituting equation 1 and 2 in equation star. So that will give us NA, the refractive index of air, which is known as 1 times sine of I, which is NB out of IB. And then if that is very true, and then it is clear to me that I will say it is equaling to NL, the refractive index of the liquid, sine R, but sine of R is the same as NB out of OB. And then you realize that this and this can excuse us. And then my NL can reduce to OB over IB. It's now OB over IB. And then I will say, for smaller angles of I and R, comma, point B will be close to any such that if these angles, we look at smaller angles of I, maybe like this as our I, you realize that point B will come very close to that. And then we can now say, if point B comes close to that point, we can now say our IB will approximately become IN, and our OB will approximate to ON. Okay? So this is also another assumption that is very, very important. You can talk about it as I being small angles, or you can say for observation made vertical above, okay, that if someone makes an observation from here, that means at this point here that is coming from what will be along that line. So all the same, or we can just be consistent by looking at smaller angles. But in this case here, the smaller angle we are talking about can be small by making observation directly above. Therefore, if you mention that, you will still be talking about the same thing. So if that is true, we'll say NL is equivalent to OB, but OB is the same as the ON, and divided by IB, which is the same as IN now. ON out of IN. What is ON? ON is this. And we have already said something that is equivalent to something we are calling real depths. Divided by IN. IN is the apparent So it is very clear that refractive index of a liquid can be real depths divided by apparent depths. So I can now therefore continue and say any L equal to real depths. What is our real depths? We can maybe say, if I'm to continue, I maybe say, let me call my real depths as T. Isn't it? Real depths T, and then I'll say it will be now T out of apparent depths. Apparent depths is this, therefore it will become T minus D. So it will be T minus D. Okay? And now from here, I can decide to cross multiply, and I say here, I have NL T minus NL D equaling to T. That is if I make decision of cross multiplying and opening the bracket NLT minus NL D. So from here now, I can now decide, maybe I can make T the subject from here. I can make T the subject here to simplify my expression, and I can say, I can now say, should I make T or I make D? Let me make D the subject. I can now say any LT minus T. I'm bringing this one this side. And then this one will be any LD. So from here I can now remove out T, and I say T into any L minus 1 is equaling to any LD. I can divide by any L. I can divide by any L. So my D here can therefore be equaling to T into any L out of any L minus 1 out of any L. That is if I distribute it to all these. And my D will be T into 1 minus 1 out of any L. So this is now the expression for displacement. When they give you the depth of the liquid and its refractive index, and then they ask you by how much will an object placed at the bottom of such a liquid of a given depth, by how much will the object be displaced? Okay, we can calculate it from here. And I'm very happy to tell you that this very same formula can even work when we are not only looking at an object placed at the bottom of a liquid, but as well if we get an object and we put a glass block on it. What is very true is that also it will also appear